My name is David Peterson. I'm the Director of Engineering Content here at Control.com, where our motto is helping engineers engineer the future. Now, if we know anything about the future of industrial automation, what we know is that it's going to demand more data, and that data is going to need to be delivered faster than ever before. Now, with computers getting smaller and easier to integrate into lots of different pieces of machinery, we're coming into this new age that we call the Industry 4.0, and one of the common terms that we hear is the Industrial Internet of Things, IIoT. In fact, that's the subject of this year's Control Automation Day 2023. We thought it would be nice to provide a small example of something that an engineer can put together and program on their own test bench to give them a little bit of a baseline understanding of all of the systems, the pieces, the hardware, and the programming at play in order to design a system like this. There's a few challenges with IIoT implementation currently, and one of those challenges is just the knowledge that's required to run such a system and to build it. Not a lot of companies have the in-house IT staff with a knowledge of both the industrial equipment and the computer equipment, requiring a networking together of both worlds that we usually refer to as operational technology, or OT. Without this knowledge, a company has to rely on an outside vendor or integrator to hopefully build and sell them the right system to collect the data that they need and to know how to use that. But if they have a little bit of knowledge already, then being able to work together with that integrator becomes a much easier task. A second problem is the cost. And the cost is not just the cost of the materials alone, but also, a lot of times with cloud systems, it's a subscription cost. The amount and frequency of data determines how much a company will pay. Do we want to be sure that we're collecting and processing the right information? Not too much, but also enough that we can make logical decisions. And along with that cost, obviously, is the time that it takes. That is a cost in itself. So we want the projects to be as quick as possible, to be as low cost as possible, but at the same time to be as effective as possible. And the only way to accomplish that is to have an idea and an understanding of how to make a system. And being able to dive into a very first project using simple off-the-shelf components is a great way to be able to learn some of the terminology and get to know some of the devices required. So to get you off the ground on this project, first, we're going to go take a look at the hardware that's required to combine the PLC system with the gateway and the cloud system that will allow us to be able to remotely monitor and send data to our system. So let's go check out some of that hardware. The basic components of this system are a PLC that connects to an HMI and a VFD, very similar to an actual production small equipment, and is connected to an IoT gateway, which is just a small microprocessor. In addition to these, the virtual component is a system that is built in the cloud with a dashboard that not only allows me to display a few basic pieces of information, but also gives me control over a couple of basic pieces of information. On my phone, I have a very simple interface. This interface has 3 push buttons, and it has 3 indicator lights. Now, to give you an idea of what's going on before we get into the components, if I press these buttons, I activate the buttons, and you can see on the HMI behind me that colored lights light up. Now, this is just an example of sending information and having it obviously received by the PLC, but in addition to this, what we also see is that on the variable frequency drive, I'm using one of the buttons to control the operation of the motor. Now, in addition to the operation of the motor, being able to control it, I also obviously want to monitor information. In fact, monitoring is often more important than the controlling of information. So if I interface with the HMI, that's what the computer is there for, I can activate these buttons, and as I see on my data dashboard, those light up. Now, the HMI and PLC are operating completely on their own network. They are networked just as a normal PLC automation system would be. It's the gateway that's interfacing with the cloud and allowing me to send information, and then also to receive that information so that we can display it on a device like a smartphone or on our web browser, allowing us to be in control of our data and our system from anywhere in the world. So let's take a little bit of a closer look at the hardware that we're dealing with in this system. The PLC that we're using is a Productivity 1000 with a little simulator input module and a combination 8 input and 8 output module. Now this might be Automation Direct, which has a specific programming, specific hardware setup. But the nice thing about this one is that since it uses discrete controls to interface with our Wi-Fi module, you can use any PLC that you want. The HMI is not meant to control the system in this case, but it provides us an easy way to create some inputs and output indicators so that we essentially have a sandbox of controls to verify that the system that we've built is actually working. In addition, we have a network switch because in this case, we have to network the HMI, the PLC, and our variable frequency drive together, and we want to connect them to the computer so that we can do programming. Now, in the case of IIoT, cybersecurity is a really big deal. So in this case, the computer network is not actually attached to our Wi-Fi module. The Wi-Fi only interfaces with our PLC system through use of some discrete controls. Therefore, no cybersecurity issues would allow anyone to have access to the network that connects our computer to the rest of the network automation system. The part of this system that's probably the most unique to most control engineers is the connection between the PLC system and the cloud. This is what we call a gateway. This gateway device allows me to interface with the PLC through use of relay outputs from the low voltage module, and relay inputs coming from the PLC allow me to interface this device, which is not compatible with 24 volts. It allows it to be compatible with a system that is dependent on 24 volts. Now this particular module is what's called an ESP8266. This one is called a Node MCU. You can take a look for this one online and they're extremely inexpensive. So this is a very low cost project to get started with. It also uses a relay board which contains 4 relays on it. So I have up to the ability to control 4 signals coming from the cloud through the gateway to the PLC. Now I also have the ability here to have at least 8 or up to 8, which is the limit on this input-output module, 8 inputs through relays going back to the Node MCU. For this project, I've chosen to only use 3 of each, 3 outputs and 3 inputs. But I have the ability to be able to do many more than that, limited only by the digital inputs and outputs on the device. Now this particular device also has a transmit and a receive, which means that it can be set up to be able to contain RS-232 communications, and in some cases, depending on the module that you're using, it might be able to talk through Ethernet using Modbus, a whole different variety of protocols. But the specific device in this case is very inexpensive, simple, and we're only using digital commands so that you can get started without having to risk the security of unauthorized access to the network of your system. Now, I'd never recommend just installing a system that you don't understand, and I'm not saying that this is exactly the ideal system that should be installed running an industrial facility, but it always helps to understand a little bit of the how and why. We've looked at the hardware, but we also have to discuss a little bit of the reason as to why would something like this be important or be a benefit to your system. So here I am in my shop at home, and at any time, I can log onto my phone, and I can either monitor the system to see whether the motor is running or not. I can also, if something happens, I can use the outputs from the phone into the system to be able to reset faults and obtain more diagnostic data. In some cases, you may not want to allow anyone, including a mobile user, to have access to controlling your system, but having access to data can be very important for diagnostics. Now, it's important to take a look at the software that's running a process like this. And in the case of this automation IIoT system, we actually have 3 different pieces of software. First, we have the PLC program, which uses familiar ladder logic, and again, we're using the Automation Direct Productivity Suite flavor of the software. But for ladder logic, you can use whichever brand you feel most familiar with. In this simple example, we have 3 inputs, the digital inputs that are coming from the PLC that are being sent by the Wi-Fi module, and those are going to the HMI, which is telling it to simply light up the indicators on the HMI. That way, if I press a button on my Wi-Fi remote control, I can see a visual indicator on the HMI that it in fact worked. Now for the outputs, I have buttons on the HMI, and I also have that simulator module. That simulator module has little switches, which could be actual physical push buttons, they could be physical sensors, and either the HMI button or these physical switches will activate an output, which sends a message to my Wi-Fi module telling it to activate the remote control indicators. I also wanted some sort of verification that the motor drive, my VFD, is receiving a command properly. So in addition, one of the outputs is connected to the VFD's return set of parameters, which if it's actual frequency, that means the running frequency of the motor is greater than 0, which means that the motor is physically running, then it'll activate the output. So when I press that button on my phone, I don't just see that the motor received a command, it actually tells me that the motor is indeed running. Now, even if I have a stop on the motor, the actual frequency, if it drops below 0, will tell me on my phone that the motor drive has been turned off. You may choose instead to have something like an alarm on the motor, maybe an overcurrent situation, or some other alarm or fault indicates a problem. Instead of the motor running being the piece of data that you want to display, you can have several different pieces of data depending on what the return back from the module is. Now, whether you're using any other brand of VFD, they all have the ability, if they're networked, to be able to send parameters and return back with actual running information that can give you a lot of diagnostic data. The second piece of software that I have is actually the console for my device, which the software that I'm using is called Blink, B-L-Y-N-K. Now, just like there are a lot of Wi-Fi modules, that Node MCU ESP8266 is just one example of a Wi-Fi connected module that can transmit and share the data between the cloud and the local system. Likewise, Blink is only one example, and when you're looking at cloud software, one of the things you need to keep in mind is how much you're being charged for amount of data. More data being submitted and returned faster will usually equal more of a subscription cost. Now, some of them, like this one, have a free tier which allows only a very limited amount of information and a limited number of controls that are available for the apps. Since this was only a demonstration, I'm fine with just a few pieces of information. Therefore, I'm totally fine with only having a very limited amount of information. And so I was able to qualify for the free tier of the software. You can certainly choose to replicate this or design a similar system on a different piece of software, but there's going to be some similarities. When you create a template, which is the physical layout of the devices, actually much like an HMI program, if you've ever designed those, we create a template and that places the buttons, the size of the buttons, the color of the buttons when they're energized, the text on the buttons, and it also connects it to a virtual pin inside the cloud database. That virtual pin, as we'll see in a second, is then connected to the physical pins on the microcontroller. Now, when you create this cloud layout, what they're going to give you is a name and an ID for the template that you're using. They're also going to give you an authorization or a device token that uniquely identifies one device to the template that you're using. So when you open up your phone, you can choose which device you're either reading or sending information to. That also is part of the payment system where free tier levels often will only support one or two or a small number of devices. If you're managing an entire fleet or an entire bank of machines, each with their own IoT device, you're probably not going to qualify for the free tier. But again, this tutorial is not meant for that scale of application. This is just to get you started with a very basic project. Now, the final piece of software that we need to talk about here is, in this case, I'm using for this ESP8266, the Arduino Integrated Development Environment, the IDE. This allows me to design a program that accesses the Blink server with the stored information in the template, and then I get to choose when a virtual pin on that database template on that server is activated, what do I choose to do with that? So let's take a quick look through here. Now, I've eliminated the token number and my own network name and password. You'd have to get a unique set of credentials for both your network and your specific device, the name of the template and the template ID. When we first connect to the Blink server, I do want to sync up the outputs from my module to the outputs that are actually shown on the app. Otherwise, I might, if in the case of a power loss and on re-energization, some of those relays may turn on and start driving the motor. I don't want to do that. So I want to sync it up so that it automatically sets the output status to whatever's showing up on my phone. So I have 100% control all the time. In this case, I have the ability to have 4 inputs and 4 outputs. That's what my template was designed for. But I created a set of 3 outputs and 3 inputs. Now, if you're familiar with this level of microcontroller programming, the input pull-up is a pull-up resistor. That just eliminates some of the hardware that's required. This isn't going to be a tutorial on how to use or how to program that microcontroller, but there's plenty of tutorials out there for both the Arduino IDE as well as that ESP8266 module. Lots of resources available online. Every second, so I don't want to be sending information constantly, but every second I write the status of the physical inputs to the virtual inputs so that they'll show up on my display as indicators. So I might have a little bit of a lag. You can change the amount of time. 1 second is arbitrary. You can have it every half of a second refresh. But that means it might take up to a second for this timer event to refresh the information. But 1 second of lag time is really not that bad for most events. I would not recommend using cloud systems for any safety urgent information or commands, because the response time, even if you set this down to almost instantaneous, there's still a lot of time that it takes to send and receive information from the cloud. So this is not usually meant for any safety devices. That's what we more call edge computing or edge timing reactions. Now, to write the information, we actually have to connect the blink write, which means I have pressed a button on my remote app on my phone, on the template, and it registers as a change on that V0, V1, and V2, these virtual pins. And as soon as that happens, I want to check the value of that pin and then send that as a command to either energize or de-energize the physical output, the digital output of the microcontroller. That energizes and de-energizes the relays, which send the command off to the PLC. So we have read and write, which are very similar to this typical read and write commands that a microprocessor program would receive, but we do have the introduction of these virtual pins, which are the connection between the template on the cloud server and the physical interface on the microcontroller. Once this is designed and downloaded, there will probably be quite a bit of debugging. This took me quite a few edits of the program to be able to get it accurate. So make sure that your system is not set up in a way that accidentally having a pin energize or de-energize would cause anything to go wrong. You might want to have this completely disconnected from your PLC, and you'll be able to see whether the relays are energizing or not. Once you know you've got it working, that's the time to hook it up to the PLC, but not before then. So there are certainly a few next steps to consider before you integrate this into a much larger program. This is great for a benchtop test to gain a little bit more understanding of the interaction between an automation and a cloud system. But first, you need to ask yourself some really important questions. And the first one is, what are you actually trying to accomplish with an IIoT system? What pieces of data are going to be the most important to really understand what's going on with your system? The sensors that you already have in place may be sufficient, but if they don't provide you that information, then you better figure that out and install the right data collection before you start trying to access that through the cloud. Otherwise, you've just lost a lot of time and the money to upload all of that information, and it's not really doing you any good. The second question is, what kind of devices are going to be appropriate for the scale of a system that you're planning? Now, what I showed you is a very simple, extremely inexpensive device, that Wi-Fi module. But realistically, a more appropriate approach for an industrial system might be to consider a device where both the PLC and the gateway are connected in the same device. Usually they'll call that an industrial PC, an IPC, which has the ability to not only run the machine task-oriented information and logic instructions, but it also has an ability to act like a normal PC, where you can download apps to it, you can connect it and configure it for lots of different either peripheral devices, including the HMIs, the VFDs, or act as the edge gateway where it can send wirelessly or through a wired network, it can share that information with the cloud. Obviously, a device of that scale requires a lot more knowledge in cybersecurity, development of an app-based environment, so there's a lot more details you have to figure out before installing something of that scale. But I hope that this gives you a little bit of a baseline of understanding of where you can go to begin to explore some options and gain a little bit of understanding about IIoT with something that's not going to take very much money and it's not going to take a whole lot of time to put together. If you're interested in learning a little bit more about the specific details behind how we did this project, then you could feel free to reach out to us here at Control.com, and we hope that an example like this helps you better understand the future of engineering and control automation and helps engineers like you engineer the future.